Thank you for this opportunity. I am Ashutosh and I am currently a postdoc at Telecom Paris. And today I will be presenting my work, Timing Advance and Doppler Shift Study in 5G NTN satellite networks. So I work with Professor Martins and Professor Bacheli. So what is timing advance? So timing advance is a standard protocol which is used in the initial access communication mechanism. Now, initial access is a process of handshaking between the UE and the base station. So it generally comprises of two broad steps. First is the cell search in the downlink, followed by the random access in the uplink, and followed by the reception of the random access in the uplink. The base station, which till that point doesn't know the location of the UE, the base station computes the location of the UE with the reception of the RACH, and then sends the uh, uh, timing advance value to the UE. And in this fashion, the base station synchronizes with all the UEs which it is connected with. Now, in satellite, low Earth orbit satellite non-terrestrial network, this process becomes more challenging because the satellite is first not stationary with respect to the UE. There is an increased path loss. The signals experience a Doppler shift. The motion of the satellite is also influenced by the non-uniform potential of the Earth. And if the UE is also mobile, then the problem compounds. And we can have Doppler shifts in the satellite base station as well as the UE. And this may also lead to handshaking problems. So we want to characterize the effect of the LEO satellite motion. We want to study the LEO satellite motion on the handshake process. The LEO satellite experiences non-uniform Earth's gravity in space, and we want to factor that in the framework. We want to study the effect of joint satellite and UE motion. And we are also capturing the underlying stochastic process in this framework. So the system model broadly comprises of a single satellite, single UE framework. The satellite is characterized by its states, which is the position, velocity, and the acceleration. The UE is assumed to have a uniform acceleration, and its states are its position and velocity. The entire analysis is performed with respect to the Earth center, which is assumed to be the origin. So the figure shows the geometry of the system. The two key angles of interest are the Earth-centered angle, which is the angle formed by the UE, Earth center, and the satellite. The second angle of interest is the elevation angle, which is formed by the UE and the tangent at which the UE is seeing the satellite. So the system dynamics can be broadly modeled as a through extended Kalman filter, which we have started to work on. So the first equation represents the motion model. The second equation represents the measurement model. Now the idea is that the states cannot be directly measured, and so in filtering, this process called filtering. And so the idea is that we measure a variable y, and through y, which is a function of x, we try to estimate x and keep a track of x. And when the f of x in 1 is not linear, you need to linearize the motion process. And this linearization we have performed through extended Kalman filtering. So the LEO satellite acceleration in space is shown in equation 3, which is non-linear to the satellite position. The motion model is shown in equation 4. So the position is influenced by the velocity is influenced by the acceleration. And we have the motion noise. So to linearize this non-linearity present in the motion model, we use the Jacobian. We need to form the Jacobian, which is used to linearize the motion model. So the Jacobian is basically the partial differential of each state with respect to all these state variables. And the Jacobian is shown in equation 7, Jacobian matrix. Now, when we consider a joint system dynamics, that is, we have the satellite as well as the UE, the state vector increases. So now we have the UE position and velocity also, in addition to the satellite position and velocity. And the joint Jacobian is shown in equation 10. The idea behind Kalman filter based Bayesian frameworks is that we have the measurement samples up to time t-1. So this is a online algorithm, and it needs to be performed at every time instant. And so the idea is that up to time t-1, we estimate the states, which is x hat t-1. Then using x hat t-1, we estimate the a priori estimate, which is t given t-1. Through t given t-1, we estimate yt hat, which is the measurement at yt. And now we have the actual observation, which is y, and we can compute the prediction error, yt minus yt hat. And then we correct the a priori estimate, which is termed as the a posteriori estimate. And this correction is shown in equation 11 through the Kalman gain. These are the equations. I'll not go into them. So the key idea is in the extended Kalman filter is that in general, the matrix A in equation 13, which characterizes the motion process, because it is nonlinear, this matrix A is represented through the Jacobian, that is F, which was constructed earlier. Now, probabilistically, this extended Kalman filter requires an assumption of the prior belief, which is the initial state PDF, which is required. The a priori belief propagation is shown here. The other important assumptions which we require is the noise PDFs, that is the motion noise and the measurement noises. And so here we illustrate the probabilistic recursion which is happening. So if we see that the a priori belief is being updated at every time through this initial condition f of x0, which we had assumed, thus showing the recursion, inherent recursion in this step. Now, what are these estimates or measurements which we are taking? So we want to track the acceleration, position, and velocity of the satellite, which are your states. And the measurement is the elevation angle, the Earth-centered angle, and the slant range. And through these, we compute the timing advance value. The elevation angle is observed to be a function of the satellite position and the UE position. These are geometrically they can also be geometrically seen. For instance, in this figure, we can observe that the gamma t is the angle subtended between the user vector and the satellite vector. And so cos gamma is the dot product of the these two vectors. And similarly, theta can also be computed with a geometric intuition. And the timing advance is a function of the Earth-centered angle, which is a function of these estimates, the satellite position estimates, which we compute through the timing advance, through the extended Kalman filter. Now, what about the Doppler shift? The Doppler shift intuitively is a function of the satellite velocity estimate and the UE velocity. And when we take these time difference of these arrivals, we get the frequency difference of arrivals, which is shown in 24. Can we estimate the clock drift as well? And interestingly, we can. Say we have an initial clock drift, which is say epsilon1, which is the initial clock drift at initial time. And epsilon2 is the change of clock drift. And in equation 27, what we observe is that the clock drift is actually can be modeled as a linear program of the slant range, which is a function of the estimates of the satellite location and the UE location. And so an accurate estimation of the satellite location, and if we know the UE location, it can also assist in a very intelligent guess of the clock drift as well. Of course, this is considering a linear program. There can be non-linearities, but this is a very preliminary study which we have started. And so the idea is that through position and velocity estimates, we can estimate the Doppler shift, clock drift, as well as the timing advance, which can be quite useful in the system design of the NTN. So we are working in close collaboration with Constellation Technologies and Operations. And we received the data of the satellite positions, velocity, and acceleration, which they plan to deploy. We received 10,000 samples from them. And the framework has been simulated for a UE, which is located at Paris. We have chosen the UE velocity to be quite high, which is approximately speed of an airplane, to test the robustness of the framework. So the first result shows the estimated and the true orbit of the satellite. The black portion, which you can see, is the visibility zone, the orbit portion in the visibility zone, which is visible from Paris region. So as the satellite will come in this black zone, the connectivity will be formed. As it leaves the black zone, the connectivity will go away. And the mean percentage error is quite robust, which is encouraging. We also showcase the variation of the Earth-centered angles and the elevation angles. The Doppler shift has been computed for two bands of interest. One is 10.9 gigahertz. Second is the 28 gigahertz band, which is of interest to the satellite operators. The timing advance estimation, figure B might be of interest, where we observe that the timing advance is maxima at the minima of elevation, and the timing advance is the least at the maximum of the elevation, which corresponds to the zenith, kind of. And this, for Paris region, we observe the timing advance to vary from roughly 10 milliseconds to 90 milliseconds. So we are now focusing on the statistical characterization of Doppler shift through stochastic geometry. And we are also working on Doppler and SNR based handovers. Jointly, we want to see the effect of Doppler shift as well on the handovers, which Sanjoy did through the SNR. We want to see if Doppler and SNR together can be more useful for the handovers. Thank you.